Welcome. My name's Nick Seward, and I'm going to be talking about this paper called There's Plenty of Room at the Top. It's basically what's going to happen if Moore's Law stalls or dies. How are we going to keep on getting performance? And the authors are a bunch of MIT professors, a guy from Microsoft and NVIDIA. So first off, I used a lot of AI. I just want to say that, but I also put a ton of human work into it, and I stand behind everything I say here. All right, what is Moore's Law? So, co-founder of Intel, Gordon Moore, in 1965, he had this idea. He saw that every year they were putting twice as many transistors on their chips. And in 1975, he revised that to say every 2 years. And it kept on going like this. He never thought it would last forever. He kind of just said, hey, I think we can do this for at least the next 10 years. He never thought it would be a forever thing. But he had this cool saying, forever can be delayed. So in 1984, people were already thinking it was dead and or slowing. And in 2000, they thought it was 10 years away. In 2014, they thought it had died again. I mean, these basically you can find an article from any year that tells you that Moore's Law has died or will die. And then the famous one recently is in 2022. Jensen, the NVIDIA co-founder, or not co-founder, CEO, got on stage and proclaimed it to be dead. But he was also raising GPU prices and needed to justify the higher price without as much performance. So is it dead? Unfortunately, Gordon Moore is no longer with us. He passed in 2023, and it was still going strong whenever he passed. And to immortalize him, I want to say this quote from him: "Whatever has been done can be outdone." Just think that's a beautiful quote. But what's the current state? Well, from this graph up to 2020, it's still going strong. There's some arguments about recent years, but there's always, for as long as I've been alive, there's always been arguments for the recent years whether it's slowing down. So, but the graph says it's going. In TSMC, the manufacturer of 90% of the advanced chips in this world, has public plans out to 2030 for 1 nanometer chips, and they have ideas of plans for 3D stacking and other things that they think can take them to 2065. So they have also a financial incentive to make people think that they have a path forward for this, though. All right, so in 1959, Richard Feynman, a really famous physicist, gave a talk about how transistors can be miniaturized, and there's a lot of room at the bottom. That's the name of the talk. And this paper is going to play on that and talk about the room at the bottom. And this paper is going to talk about room at the top. So the room at the bottom was making transistors smaller, and we've done that. That's what Moore's Law is. And the room at the top is dealing with software, algorithms, and hardware architecture. So to talk about software, let's talk about some bad software, and then we'll make it better and better. So here's some bad Python code that will do matrix multiplication between two 4K matrices. And you shouldn't write Python code like this, but it is. If you want code to go slow, that's not very efficient, that's the way. And we get 7 hours, and it's only using 0.0006% of the max number of gigaflops that processor was capable of. Java goes to 40 minutes, and C goes to 9 minutes. This is the same code, same algorithm, just different, just translated. If you add threading, you get like an 8x speed boost, which is strange because there's 36 cores on the test bench that they had, and you would expect potentially up to 36 times faster if you can utilize all the cores. But something's going on that keeps you from doing that. You can't always parallelize to the nth degree. Another technique is you can chunk it up where you can do sub matrices and where they can fit completely into the cache, so you don't have to keep on going back to the memory, and you can just keep it completely in each of the core's caches, making things go a lot faster. You go from 1 minute to 4 seconds. And then you can line up a few pieces of data, and you can do calculations on all of them at once with what's called a SIMD instruction, or a single instruction multiple data instruction. And Intel has provided even fancier SIMD instructions. They have what's called the advanced vector extension, which lets you get down to 40 milliseconds. Pretty good speed up. That's 60,000 times faster from the top from Python all the way to optimize C code. But that C code is going to be really nasty, really long. I just want to point out. So I just want to, for my own benefit, I want to redeem Python. So here's some Python code I wrote in the modern era, and whenever I benchmark it, I actually went to AWS, which is what they used, and Amazon Web Services, and I used the exact same machine setup that they used, and I did a little research, and I saw that they actually didn't use the latest and greatest at the time. There's actually a thing called AVX2, which lets you stack up twice as much data before you ask it to process that data. In theory, what they thought was a machine that can only do 800 gigaflops can actually do 1,600 gigaflops. Which made me have to modify all these percentages. And so my Python code that utilizes all the latest and greatest can still only use 40% of the CPU, but I got the runtime down to 200 milliseconds. Okay. Well, back for a second. I want to talk a little bit about gigaflops. So I'm saying the word gigaflops. That stands for billions of floating point operations per second. And that makes me think of supercomputers. I read all these articles back in the day. So I did a real quick calculation just to give you some context of where we're at Moore's Law wise. So I just bought a laptop with a 3050 RTX that's capable of about 6,000 gigaflops. And if you rewind 20 years, that 6,000 gigaflops would make it the 20th most powerful computer in the world. It would be a top tier supercomputer 20 years ago. Crazy. Okay, so some people think that to get performance you have to know all the tricks, and you have to have C code, you have to do all the special things. But I think that's a misnomer. Like my Python example shows, I'm using libraries and I can squeak out a ton of performance. But Python's still bad. But you can make vanilla Python even faster. There's a thing called Mojo, which is a superset of Python that can compile down into machine code. Chris Latner, he's the guy behind Swift and the LLVM. He was like, people like Python. I don't particularly like Python, but people do. So let's meet people where they're at and make Python compile down to machine code. So he actually invented a thing called intermediate representation that sits on top of the LLVM. Since he knows how the LLVM works, he was like, I can't get Python all the way to it, but I can get it halfway there. And so he basically made this intermediate language that Python can compile to, and then that will run on the LLVM. And you get C speeds, you got memory safety, you can do all the things. You get cool things like auto tuning instead of having to manually tune things and get it to match whatever hardware you're running on. It does some amazing things. I encourage you guys to go watch Chris talk about this. Relevant to UA Little Rock, I teach Programming 1 and I teach C++ right now, but I want to move that to Python. But the argument would be that's not fast enough. But Mojo would be. It's not ready today. It needs to mature a little bit and get all the edges knocked down. But it's usable today. It exists. This Mojo's going to happen. It's amazing. All right, software reduction. So we're moving on to a different domain. We're going to talk let's say you want to make a program that can recognize whether somebody said yes or no. And the normal process would be you would go pull out a speech recognition library, and you would have it recognize the words and then just check to see if it's yes or no. Easy peasy. It's easy for the programmer, which is great. But what's horrible is the speech. Like, you have to have the whole library, and it's doing a lot of complicated recognition tasks whenever you just want to know if it's yes or no. You could definitely, like, if you knew how speech recognition worked and you learned all that stuff, you could build your own solution that would be like thousands, millions of times faster, possibly, if you only wanted to do yes or no. So there's a lot of performance left on the table as you translate from one type of problem to another. So we're translating just like classify yes or no to just get the word. We have a problem we don't know how to do, and we mapped it to a problem we do know how to do. And every time we do this translation from a problem we don't know how to do to one we do know how to do, we add inefficiencies. The speech recognition library, I'm sure, does it also with things even lower down in the stack. So that is hard to fix and I think we need automation for that. The book, the paper talks about it a little bit, but they don't have any really clear solutions. Let me just spitball like a wackadoodle naive research project that could potentially start trying to solve these problems. But, again, this is just a very naive research idea. What if we could take all the source code, you gather up everything, including all your libraries, you somehow trace through, see what's actually actively being used and what isn't, and you condense all of that down. And then before or after, and manually or automated, you build a bunch of test suites to verify everything's doing what it needs to do and in the correct way and all that good stuff. And after you do all of this, all of that can be done without any AI intervention. But then it's hard to manage this crazy, complex, billions, millions of lines of code, whatever. So then you have AI suggest improvements. And for whatever you want to optimize on. Do you want it to be faster? Do you want it to be easier to read? Do you want to have less functions? Whatever you want to optimize on. So you optimize on that. Then you run it against the automated test. And if it doesn't pass, you revert or ask it to fix it. And then once you get a successful improvement, then you just iterate over and over again until you get diminishing returns. So anyways, crazy idea, maybe could work. I did a little bit of research. I don't really see anything like fully this cool. But again, this is really naive. But anyways, if you want to work on something like this with me, hit me up. I'm definitely kind of keen to do a little prototype on maybe just some Python libraries, but yeah, I have no way of doing this on a large scale yet. So moving on to algorithms. So I have this cute little robot here, and he's pushing on the door, but it says pull. So he could get through that door if he pushes hard enough, but maybe you could just pull on the door and go through. That's what we're talking about. We can work harder, or we can make the job easier. So we can always find a way to be lazier as computer scientists. So we were talking about matrix multiplication before. The current algorithm takes into the third calculations to do it, but there's a state of art one that can only take in being the size of the matrix to the 2.3. That's like a lot less calculations. That's 186 times less calculations. But nobody implements it. It's too complex. There's constant time cost. Even in like custom hardware, they're only using the naive into the third approach, which is interesting. So, which makes it sound like we shouldn't do algorithmic improvements. But here is an example of one that does work. Here's an example of a network where we're trying to figure out the max amount of flow we can get from the S node to the T node. It's called there's a bunch of max flow algorithms. And of various efficiency. And here's a map of them over the years, a graph of them. And so you can see we've had improvements. The last one happened in 1998. We got the Goldberg-Rao algorithm that lets us do it really, really fast compared to the original Edmonds-Karp one. In fact, if we were to fast forward from now, it would take 25 years for Edmonds-Karp to match with the performance of our current state-of-the-art algorithm. So what I'm saying is we, with algorithmic improvements, in this case, we jump 25 years in the future, where if we didn't have any algorithmic improvements, we would have to wait 25 years to get more capable processors, with assuming Moore's law holds. All right. So the book makes a point about three things about algorithmic improvements. It's going to be uneven and sporadic. You never know when there's going to be an advance. Those gains can way outstrip Moore's law, and you're going to eventually reach like you can't improve forever. Like at some point, there's a theoretical best algorithm. We might not know that, but as we get closer to that performance, we can't go past that. We can't break the laws of nature. All right, so that ends talking about algorithms. Now we're going to move on to hardware and the ways we can use that to keep on getting more performance. So the first thing is clock speeds have stagnated. We need to figure out how to do more with less. And so one easy way we can do that is we can, instead of having one big processor on a CPU, we can have a bunch of little processors that are all doing things at the same time. So we can just basically, we want more transistors to be working at a time. And so do more with less. So beyond parallelization, we can have specialization. So we have lots of different tasks that we want to do. That if we do it on the CPU, we'd have to have a crap ton of CPUs, or we can have a specialized piece of hardware on the die that could be much smaller than all of those CPUs would be. So we can specialize and do special tasks. We have to balance. But when we're not doing that special task, we don't get to use that part of the die. So we have to balance it a little bit. So anyways, one big thing is AI cores. AI is starting to get built in everything. It's basically doing big matrix multiplications, and so people are building that right onto chips nowadays. GPUs, we've had those for quite a while. Those were specifically for graphics at the outset, but like we figured out how to use them for more things. We've actually dialed back the specialization a little bit using libraries like CUDA, allowing us to do scientific calculations, and general software can now use GPUs a lot more effectively than they could in the past. And then media encoders. Say you want to compress a bunch of videos, like you build a special part of the chip that does just that instead of wasting a bunch of cores and CPU cycles. So here's a Snapdragon 820 from 2015. This shows you roughly how much of the chip is taken up with different things, and you can see a high degree of specialization. You got CPU, graphics processor unit, display processing unit, image signal processor, digital signal processor, and video processing unit, which does compression. And then, so all of these things do their own thing, and and this kind of matches with the things that a smartphone does. This is a mobile chip, and so you can see smartphones do video, do images, and they have die space dedicated to the uses that a smartphone is going to be used for, which is great. You can also see here we have connectivity and memory. You have to have memory, and you have to get a way to get that memory around, that data around the chip. And I want to make a point about locality right now. And as you have more and more cores, they have to go to the memory, get the data, and then give it back at some point. If you don't have any way to store the data locally, you're going to have to keep on requesting the data back and forth from the memory, and the connectivity layer is going to get bigger and bigger and more bogged down, having to keep on going to the centralized place for memory. And so what you can do is you can build into each of these subunits, these cores, you can build in their own cache. So memory can go from the main memory to the cache, and you could do all your processing where it's really close, small connectivity, small connections. And then when you're done, you can send it back to the main memory, which could be a ways away. So you have to balance that. You can cache is very expensive, but also is making really fast buses for the memory. So, okay, next thing is you can do simplification. So you could make your cores smaller and simpler, which seems like it's going to make it less capable. But if you get rid of a big core and replace it with numerous small cores, a lot of tasks that you want to do can fit on a small core. And so the small cores you get from getting rid of a big core can outstrip the performance from just that one big core. And so this hybrid architecture is being taken on by Intel, ARM, And for a while, AMD was resistant. They were like, "We have only performance cores. Get our chip. We'll have the max performance because we don't do these efficiency cores." But AMD is now working towards having E cores or efficiency cores on their machines. And so I talked about this a little bit before, but you got to balance it. You got to figure out what your chip's going to be used for, and you need to optimize for those uses. And we have really good tools for that. And you can see from that mobile chip I showed you earlier, we have a lot of specialization, but it matches with the need of the chip. So you don't over specialize because you don't want transistors to sit there idle. All right, that brings us to the end. So the challenges we had to address were software has to be tailored to the hardware, and getting rid of problem reductions is a yet to be solved problem. And I was just mentioning maybe we could use AI to help with that. Maybe we can build better software libraries that can somehow plug into what's above them to help with reduction. I don't know. There's some technologies that are yet to be created in that area. Algorithms will happen when they happen. They're great. They're amazing. We can't really those will happen when they happen. Anyways, then hardware. We're already doing it. Lots of specialization. Move memory to where it's being used. Simplify your cores so you don't have to waste big cores on simple tasks, and you can have more cores do more work. So that's what the paper basically focused on. Lots of room at the top, but moving forward, what kind of technologies are there that are on the horizon that maybe even can help with Moore's law to continue? And TSMC is actually doing this one. So this is not this. I mean, it is emerging, but it's pretty much going to happen. That is 3D stacking. And so as you make transistors smaller and smaller, you get to a physical limit, a physics limit, law of nature limit, where you can't make transistors smaller than an atom, for instance, at least that we know of. And so you can trade that law of nature limit for a engineering limit by going from 2D to 3D. So you can stack up bigger transistors, but just in 3D. And the problem is it's hard to get power to them. It's hard to cool them. But those are engineering challenges, not having to rewrite the laws of physics problems. So TSMC is already working on that. Quantum computing is just mind-boggling. There's a whole class of problems that it can solve in sublinear time. That means for the size of your input, if you have 1 million items and say it takes you a second, if you double that to 2 million items, it's not going to take 2 seconds. It'll take less than 2 seconds. The scaling is great on these quantum computers, and you can solve all sorts of problems that we have sometimes intractable solutions to. So like scheduling is almost impossible for us to do without some major heuristics, and quantum computing can just do that in sublinear time. You got simulations, you got factoring, you got solving systems of linear equations. The list goes on and on. Quantum computing is going to blow the top off of everything if it happens. But it's always like 10 years in the future when quantum computing is going to happen. And Moore's law is always going to die in like 10 years. So maybe when Moore's law dies, quantum computing will be around and we'll keep on going. And we might get fusion power too. Who knows? All right. And the last one, this one's crazy. This is all very speculative, but if you have like nanotubes and graphene, you can make transistors that are like, molecular. And if you take a cubic centimeter and you cram as many transistors in there as you could possibly cram in there, you'd get 10 to the 18th transistors, or 1 quintillion transistors. That is 1 trillion times more transistors than the computer I'm working on. That is 10 trillion times more transistors than the human has neurons. So I would think you could probably simulate a human on one of these, or multiple humans on one of these. And Anyways, that's just wild. And if Moore's law continues, then we would get this cubic centimeter of amazingness in 2100, only like 75 years in the future. That's wild. Obviously, lots of engineering challenges to solve to get there. All right, so if you have questions, go put those in the comments. I have a link to the slides here. I have a link to all the sources that I have. So thanks for watching, and hopefully you agree that there's more room at the bottom and definitely a lot more room at the top.